This is a great series. They're asking, does it converge or diverge? The very first thing I'm going to do here is a divergence test, but it won't work because the limit as n goes to infinity of that tan of 1 over n. Let's see, that'd be tangent of 0 essentially, which is 0. And so that doesn't work out for me. If I tried the ratio test, and I'm not going to be too, uh, what is it, rigorous about it because it's not going to work, but I'm just going to showcase if I tried that ratio test, it would actually be 1 as I let the limit, as I took the limit as n goes to infinity, which again will not work. Root test obviously will not work here. Integral test might work if you tried the integral test, but man, that's a pain. So I'm really thinking I want to use a comparison. And this is going to be, or sorry, the tangent function is going to be tough to compare to if I used a series comparison. But if I did a limit comparison, I would love to compare to that 1 over n. So let's take a limit comparison test to the series 1 over n. Or in other words, we're going to let b sub n equal 1 over n. Now remember, to use a limit comparison test, you need both of your series to be positive. Well, b sub n is already, or all, both your sequences to be positive. B sub n is already positive. And tangent, so note, tangent of 1 over n is actually positive as well. That's because you're starting at 1, so tangent of 1 is going to be positive if you think about the graph of tangent. And then as n gets large, you're plugging in numbers that are getting smaller than 1. And if you think about the tangent curve, it's always above the x-axis, no matter what numbers you're plugging in, as long as you're positive there, and it's approaching 0. So the tangent function is going to be positive. So we have two positive sequences. So I'm going to compare. And by the way, note again, the summation 1 over n is a divergent harmonic series. I don't even need to say why, because that's just a very special series. We should always know that that diverges. It's a divergent harmonic series. So now I'm going to take the limit as n goes to infinity of the ratio of those two. I'll put the tangent in the numerator, but it doesn't really matter. That's supposed to be an n there, sorry. Now, if I'm really going to be exact and rigorous about that, all those n's should be x's. If I'm really being rigorous about it, because honestly, we're about to use L'Hopital's. So if you take a look at that as x goes to infinity, that's going to be 0 over 0. And so via L'Hopital's, that would be the limit as x goes to infinity. The derivative of the tangent is the secant squared. The derivative of its interior is a negative 1 over x squared. Downstairs, the derivative of 1 over x is a negative 1 over x squared. And this is the limit as x goes to infinity of secant squared of 1 over x. And that'll be secant squared of 0, which is 1. Now remember, limit comparison test means to make it work, we needed that limit to become finite and positive. This is definitely finite and definitely positive. Therefore, both sequences that, or both series really, that we're looking at, the tangent of 1 over n and then 1 over n, those will converge or diverge together. Well, because we already know the summation of 1 over n diverges, that implies the summation n equals 1 to infinity of the tangent of 1 over n also diverges. And that's by limit comparison test.